So now we're going to come up with the Chezy formulas, which are just some nice simple equations that we can use for open channel flow when we can assume 1D uniform flow, fully developed flow. So pretty much our simplest case. So what we're going to do is start with the energy equation, and that is P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2 plus HF plus HS. Alright, and I'll skip minor losses, we won't include those. So let's get rid of HS right away. We don't have any pumps or turbines. In open channel flow, let's use the free surface as our streamline. So always put your 1 and 2 at the free surface, and that means P1 equals P2 equals 0. Yay. Cancel. Also, for fully developed flow, what that means is V is not changing from 1 to 2. So V1 equals V2 equals V0, you can call it. Well, if V1 equals V2, then V1 squared minus V2 squared is 0. These will also cancel. All right, and what we have left is then just Z1 equals Z2 plus HF. Nice and simple. And we can rewrite that as HF equals Z1 minus Z2, or delta Z. All right, so if we draw a picture of that, again, these things are typically gravity fed. So we're going to have a theta. Here's our 1 at the top. Here's our 2. And between there, we're going to say we have the distance L. Okay. This distance is the vertical distance. That's our Z1 minus Z2, right? So this is also theta. So we can say our HF is actually L times sine theta. All right. So turns out a lot of times it's just easier to measure tan theta. So what we're going to do is we're going to define a value SO or S0 as tan theta. And it turns out if the angle is small, then tan theta is approximately equal to sine theta. And these angles are all going to be small. You wouldn't have a channel that's going like straight down. So if that's the case, we can say our HF is actually SOL. Okay, where again SO equals tan theta, or sine theta, approximately the same. Okay, so energy equation gave this a nice simple equation for head loss. We can also use our head loss equation that we had from internal flow, and that was HF equals FLV squared. In this case, we'll just call it V0 squared over 2D, and this time we're going to have to use hydraulic diameter times G. Okay, but in an open channel flow, we don't want to use hydraulic diameter, we want to use hydraulic radius. And DH equals 4RH, so we can actually plug that in and get HF is equal to FL V0 squared over 8RHG. All right, so with this equation and this equation, we can now solve for velocity. So SOL equals FL V0 squared over 8RHG. And solving for velocity, V0 equals, and we want to write it out like this, 8G over F to the 1/2 times RHSO to the 1/2. And we want to write it like that because what we're going to do is combine this Hg over F to the 1/2 into Chezy constant C. And then times RHSO to the 1/2. All right, so that gives us velocity. So we just use the energy equation and our definition of HF that we had before. Okay, at this point, we could use Moody and find an F, and that would work out. Flow rate then, flow rate is easy. Flow rate is just Q equals VA. All right, so that is going to be C A RHSO to the 1/2. All right, so remember, whenever you have an A here, when you just see A, use the real area, cross-sectional area. Don't use pi RH squared. So now we have equations for velocity, for flow rate, and for frictional head loss. So let's go on, and we can use conservation of momentum for finding something about shear stress, which is very important for erosion and that kind of thing. So first thing in our conservation of momentum, let's go ahead and draw ourselves a control volume. So here is our channel, and it is on an angle of theta. And what we're going to do, since we want to find shear stress, we are again not going to cut right through the surface. We're going to leave our control volume right inside the bottom here. So here we're going to call this length. We're going to call this our inlet, this our exit. And inside here we can already start drawing a free body diagram. So we're going to have weight, and we're going to have shear stress. This shear stress really is along all the surfaces. Let's call it not stress, but force due to shear. All right. We are also going to have pressure, but if you look at this, this is the same velocity on both sides. The pressure is going to go out to in, so there's no big hump here from a wave, so it's going to be the same pressure on both sides. So let's just say those are going to cancel out and we won't draw them. So our conservation of momentum equation then is, remember all our forces, sum of the pressure forces plus gravity plus shear plus other, these are all vectors, equals, and we have one inlet and one exit like that, m dot v2 minus v1. All right, so right off the bat, even still in vector form, and these should have vectors on them as well, we can cancel a few things. For one thing, we're not cutting through any surfaces, so no other. We just said we're going to cancel the pressures. Other thing we can cancel, because this is fully developed, uniform flow, no humps in the middle, no area changes, velocity 2 equals velocity 1. So that whole term's going to go away. So what we're left with is just gravity equals shear. So now let's just do this. We want to break it into components, so let's just do this in the flow direction. I don't want to call that x because x in these problems is usually horizontal. Our flow direction is not, so let's just do this in the flow direction. And what we have is, okay, our W will just have one component in the flow direction. Let's say it's going this way. And that is W sine theta, right? So W sine theta. And then our shear is going to be then just minus F shear equals 0. Okay, so now we can do some substitutions because that is a terrible theta. It's not easy to write with this little pen on this tablet. Anyhow, let's do some substitution. So our W, the weight, is the weight of this whole fluid. And the weight of that fluid is equal to rho G times the volume of that fluid. And the volume of that fluid, so rho G, is just going to be this cross-sectional area times this length, AL. All right. So let's do some substitutions for shear. So our F shear, if you remember, shear stress is force over area, which means shear force is your shear stress on average times your area. But what area is that? Well, that's not our cross-sectional area. That's wherever our fluid is rubbing against walls. Okay, so that's the surface area, let's call it. Surface area. Okay, and your surface area then is going to be, so F shear here is going to be your tau average times the perimeter that's touching the walls. Remember that wetted perimeter? So if we go all the way around here, down into the page, and then back up, that's our perimeter, and then times L, and that gives us our whole surface area. All right, so let's put this together, and what we have then, this equation is rho G A, where A is the cross-sectional area, L sine theta minus tau average PL equals 0. Well, the L's cancel. Another thing we can do is for small thetas, sine theta is about equal to tan theta, and that is equal to our little SO we talked about before, so we can plug that in. And so what we're going to get here is, let's solve for tau average, the average wall shear stress. Tau average, if I pull it over here and then divide through, we're going to have rho G A SO divided by P. Okay. Do you remember what A over P was though? Rho G A over P was our hydraulic radius. All right. So there it is. That's our tau average. You just rewrite it again. And that came from conservation of momentum, rho G R H S O. All right. And then let's just summarize these equations that we got so we have them all in one place. We've got velocity is equal to C times RHSO to the 1/2. Our flow rate is equal to CA RHSO to the 1/2. Our shear stress on average over all those surfaces is rho G RHSO. And we also had that our HF, if we want this in head form, is SOL. All right. Also, this C value here is equal to 8G over F to the 1/2 power, square root. Okay. That's it.